Okay, in chapter 2, we're going to talk a little bit about the origin, composition, kind of structure of the atmosphere. So, we're not spending a lot of time on the theory of how the atmosphere was origin. Just a little bit here to give you a better idea. Well, one of the things I wanted to show you was the atmosphere is connected all over the world. So, for example, in the summertime especially, there are dust storms that develop over parts of the Sahara. And this dust is transported and it can actually come all the way into the southern United States. Guess what? You saw a perfect example of this the last week when everything was so smoky. Baseball games and outdoor events were being canceled across the northeastern United States. And yet, the problem wasn't in the northeastern U.S. or the eastern U.S. The problem was in Canada, where the fires were. They were putting the ash and the smoke in the air. It was being transported down across our area. That's just an example of how interconnected we are. Dust can definitely. So, weather can change in an instant. It can go from a very bright, sunshiny day to a severe weather day. So, when you think of the Earth system, and this is the Earth system, it consists of the atmosphere, which we are going to be studying, the hydrosphere. Guess what? The hydrosphere plays into the atmosphere. Hydrosphere is water. So, all the oceans, lakes, rivers. Where does the moisture come from in the atmosphere? From the hydrosphere. Geosphere. What is the heck is a geosphere? Well, it's kind of the Earth crust, things like volcanoes, and all are the geosphere. And guess what? Volcanoes can impact the atmosphere. So that is how we're related again. That go back and forth hand in hand. The biosphere is us. It's living creatures, it's plants, it's animals. And yes, plants, photosynthesis is a great example of how they impact the atmosphere. And the atmosphere is relatively thin. Half of the mass of the atmosphere is within 18,000 feet. A little bit over 3 miles up, and you go through the whole atmosphere. And it's very homogeneous, the lower part of the atmosphere. In other words, if I told you at the surface of the Earth, we have roughly 21% oxygen in that part of the atmosphere. No trouble breathing, is it? Hey, now go to the top of a mountain, say 10,000 feet up. Well, there's a lot less molecules. The atmosphere is spreading out. There's not as much weight there pushing the atmosphere down. But we still have 21% oxygen. It's just there is not as many oxygen molecules. That's why you get winded very quickly when you're up in higher elevations. When you get above about 80 kilometers, gases kind of separate out. That homogeneous part of the atmosphere doesn't really work too well, but all weather is pretty much below that. And here you can see the oxygen relationship. There are aerosols in the atmosphere. Come from dust, water vapor, carbon dioxide, pollution, both man-made and regular. Studying the atmosphere, we use something called the scientific method. You've all heard this through high school science, through probably even in elementary school science. All that is to say, okay, we look outside or we look at something and we say, I wonder why that's occurring. So we ask a question of it. I'll give you an example here that we dealt with at my office. We have thunderstorms that develop across West Virginia, across Ohio, that area, that move east. Not every time do those thunderstorms make it across the Appalachian Mountains. Why is that? What is causing that? So it's a question we posed. Why do those thunderstorms not make it there? And we came up with the hypothesis. So we came up with that hypothesis, then we said, well, let's check that hypothesis. Turned out, not all that hypothesis was that good when we tested it. So we redid it, changed the analysis, changed the hypothesis. And then we started getting some real answers that actually worked. We were able to make a forecast that could say, thunderstorms are going to actually increase when they get on this side of the mountain. They did. Oh no, the thunderstorms are going to decrease, and they did. So now we had a new tool in our tool chest to forecast the weather, and that was how we used the scientific method to get to that point. There are other things looking at atmospheric models like vortex chambers, numerical the models. Everything I'm going to talk about has a numerical model equivalent to it, or equations that govern it. We're not getting into any of those equations. You can be thankful. But they're there. They're the underlying of every numerical model and every forecast that the Weather Service or anybody issues is based off of these mathematical equations. Unfortunately, they can't be solved. Nobody's developed the system yet. We got to observe the weather. We just talked about that earlier, and one of the greatest tools is the automated surface observing system. It literally takes a constant picture of the atmosphere wherever it's located, and it's located at almost all airports. Why is it at the airport? Pilots need to know what they're landing into or what they're taking off from. So the Weather Service and other agencies partnered with these airports, and even smaller airports have systems like this. And they're literally constant. So I can go back and look at a graph that shows the temperature change literally within seconds and see how it worked throughout the day. How did it go? They're a cooperative network. CocoRa's is another example of that look at more longer term, but they can, volunteers are great. They fill in the gaps. ASOS is only at the airports. Well, heck, there's not an airport in every little town, nor is there an airport maybe in hundreds of miles of each other sometimes. These observation networks, community networks, fill in those gaps and help us to determine what the weather is. Radiosondes, they're just a balloon. Hydrogen used to be hydrogen, now it's helium mainly, that goes up into the space and eventually bursts. Why does it burst? The pressure in that balloon was taken at the ground. As it went up, remember, the pressure is getting less and less the higher up you get. So the balloon is just going to expand, eventually break. But as it's going up, it gets a vertical profile of temperature. Dropsondes, opposite direction, or dropped out of an airplane. Very similar instrument, but now they're going down into the ground. Many times they're dropped over the oceans with Hurricane Hunter aircraft looking at hurricanes, maybe looking at a large low pressure systems. Another great tool, radar and satellite. Both of them are fantastic tools for looking at the weather. Here you can see an actual temperature profile. Notice temperatures decrease with height in the troposphere until you reach the tropopause. So the higher up you go in the troposphere, typically your temperature is going to be lower. So if you're walking up a mountain, when you get to the top of the mountain, the temperature is lower. Last summer, I took a trip out west. I went to the Rocky Mountains. I started my day at about 7,000 feet, wound up my day at about 13,000 feet. Guess what? It was a heck of a lot colder at 13,000 than it was at 7. And if I had been even down into Denver, which is around 5,000, it would have been even warmer. More of a drastic change. The ionosphere and the auroras, if the solar wind's blowing, the stronger it blows, the more the auroras, more active they are. And you can see they expand outwards. So with all of this, just wanted to give you a quick view. We talked about the vertical extent. Well, here is a sounding. So all this is a plot of temperature on the right in red and dew point on the left. Remember, dew point kind of represents moisture. The closer they are together, the higher the relative humidity. This is Cincinnati, Ohio, or Wilmington, Ohio, actually. Very close to Cincinnati. And you can see it got colder all the way up to right here. Pressure at this point is about 175 millibars, we'll say. And all of a sudden there, it started getting warmer. That is where the tropopause occurred and the stratosphere began. So you can see how that changes with height. Now I wanted to show you an upper air map where you're going to be seeing these throughout the course. Don't get alarmed at them. They are just station plots like we saw at the surface, except for an upper level of the atmosphere. This is at 500 millibars, halfway up, 18,000 feet approximately. And you can see there's low pressure out here, another low pressure here, high pressure in the upper Midwest. So these are your flow patterns aloft. So if I was to look at this and say, oh, well, the winds are out of the west here, northwest here, look at the surface. Oh, gee, I've got south winds here. They're not westerly. So you can see the winds did change with height. So hope you got a little bit out of this. Let me know again if you have any questions.